Hi there, welcome to the April Fool's Day edition of the 3220 video lecture notes. Today we're starting on a new chapter. This is chapter 6, which is the sampling of continuous time signals. Now this really kind of brings together a lot of things we've mentioned in the past, but we've never really focused on. We have discussed so far the ideal sampling of continuous time signals. Okay, what I mean by that is that we've found that x of t, make that, where's my eraser? I didn't mean to say that. X of n which is the discrete time signal, can be derived from the continuous time signal by letting t equals n times big T, where big T is the sampling interval. Okay, so that just means that x of t is a variable that's continuous, it takes on all possible real values, but now we're just going to look at it at every t seconds. We're going to check out its amplitude and store that as the nth sample of this discrete time signal. Okay, but there's things that we haven't really focused on. We've kind of mentioned them briefly in passing, but now we're going to talk about a few things with some detail. And one of those is how exactly is the spectrum of x of t related to that of x of n. Again, it's something we've kind of mentioned, but we haven't really talked about it and given the details. Well, that's one thing. Another thing that we've mentioned in passing but not really talked about is how can we recover, let's see, how can we recover the original signal given the sampled signal? Okay, so this is the real key to using computers to process like voice and develop communication systems. Is we take we want to do this on a computer, but we have to not only go to x of n, but then we have to go back to x of t. And the final thing that we're going to start talking about in this chapter is practical ADC. ADC is a very common abbreviation for analog to digital conversion. Okay, so those are the things we'll talk about today. I'm going to do a slightly different development than the book does. Hopefully, two different ways of looking at it will help you understand. If one doesn't work, then the other doesn't. Then the other will. My approach I'll give is maybe a little more visual and maybe a little less mathy. Still going to be some math, as you can probably guess, but hopefully that'll lead to something that's easily more better understood. Okay, but I'm not sure. Read the book, read my approach together. Maybe that'll help you understand what's going on. I'm going to use a little bit more simplified notation than the book uses, and I'm going to do this temporarily, but it'll speed things up. So notationally, at least for a while anyway, where the book is using x of j omega, I'm just going to write x of omega and assume that we understand that it's evaluated on the j omega axis. And similarly, when the book writes x of j to pi f, I'm just going to write x of f. Lots of books do this, and this is maybe a little. I understand why the book's doing it, but for purposes of shortening the discussion, we'll just use this. Another thing is, I'm going to try, at least today, I'm going to try to, when there's a capital X to indicate we're in a transform domain, I'm going to try to write a little bump on the end of the x, because my lowercase x's and my uppercase x's tend to be real similar looking. All right, well, with all that out of the way, let's look at this simplified model of sampling that I'm going to use here for a minute to try to explain what's happening. So here's our model. Okay. I'm going to say that, to begin with, our original signal is just something that looks like that, and I'm going to refer to this as x sub c of t, and the c refers to continuous time, and you'll kind of see why I'm bothering to put the subscript on there, but it'll be clear in a minute. So x sub c is the continuous time signal that we're going to sample. Okay, I'm going to multiply, I'm going to represent sampling as a multiplication of the original signal by what's called the ideal sampling signal. That's a times. I'll put it in a circle. And this is S of t. Okay, and what it is a bunch of delta functions, a train of delta functions. I won't bother to write the little pointy ends on the delta function. So S of t is called the ideal sampling function. Okay, it's just an impulse train. Train of impulses, right? And these things happen every t seconds. So just at the end, the impulses occur at the sampling rate. So if this is 0, then this is t, and this is 2t. You can read my writing, etc. So all these, of course, that's the time axis. And if I multiply those two together, I get the sampled signal. Now this is an analog signal, continuous time signal, but I'm going to call it x sub s of t, and it's going to look like this. It's going to have the basic envelope of the original signal that we're sampling, but it's going to have, when you multiply this times this, it's going to be 0 everywhere in between these impulses, right? Because it's 0 times the signal is equal to 0. But at 0 and t and 2t and 3t and so on, we're going to have an impulse, and these are delta functions, but they have unit weight. So unit weight delta functions times xc of t is going to give us an envelope that's made up of delta functions. So it's going to look like this. Okay, and again, we're gonna sort of gloss over the fact that these delta functions go up to infinity, and just like is standardly done in most books, we're gonna say that the height that I draw them is equal to the weight. Okay, like that. So again, these are 0, t, 2t, etc. Like that. So that's the sampled, that is the sampled signal x sub s of t is the sampled continuous time signal, it's equal to x sub c, the original signal, times s of t, the sampling signal. So that's our model of sampling. And you notice that this result is still in the time domain. It's still in the t domain. It's continuous time. But now we've sort of represented the idea that we're picking up the values of xc of t at these sampling intervals. What this does is it's very good as giving us a model, to math model to understand the spectral issues, spectral properties of the sampled signal. Okay, so we'll be able to easily find the spectral properties of X, the sampled signal. The next thing, what it doesn't do is it doesn't really tell us what happens when we go to discrete time. What happens when we go from x of t to x of n. Okay, this turns out to be, we'll treat this separately. This is a time scaling issue. We're going to treat this as two parts. One where we look at the spectrum, and the other we'll look at the time scaling. When I say time scaling, let's just give an example. Suppose we just look at the interval from 0 to 1 second in continuous time, and suppose that the sample rate is 1,000 samples per second. Then the new time variable n is going to range from 0, n, to 1,000. We can see that the original time scale, t in seconds going from 0 to 1, now gets transformed into a new time scale, n, going from 0 to 1,000. Well, this is a completely, we've scaled it up. It's a linear time scaling, but we've scaled it up. So these are on different time scales. And so we expect that we'll get some frequency scaling as well. So we'll do this in two parts. We'll look at the spectrum of this thing, and then we'll see what happens, the spectral shape, and then we'll also have to see what happens along the frequency axis.